Okay, welcome back. So as you remember, last time we derived a new formula for conductivity, and that new formula, we call it the semi-classical or the quantum formula for conductivity. That formula included this quantity, which we call capital N of E, following our textbook, and we call it the electron population density. So that's a name for it, but we need to find it. We need to shed a little bit more light on what that is and what it depends on. So that is going to be the main objective for today. Okay, so the formula that we found was this one here, the 1/3 E squared tau V sub F squared times this electron population density at the Fermi energy. So this is not a product, this is a dependence, right? So this population density depends on the energy, and we want to evaluate that function at the Fermi energy. So what is it? Okay, how can we compute it? We need to know that because otherwise we can't evaluate the conductivity. So as we said, we'll call it the population density of electrons. Okay, so we also said that in terms of its units, it is the number of electrons per unit volume per unit energy. Okay, so this whole discussion now, this whole treatment will take us a little while to fully complete. The results will be useful for us, not just in terms of the conductivity formula, but also in terms of our next big topic in the course, semiconductor physics. So it is well worth the effort now because it is not just applicable to this particular formula. That would be sort of a narrow application, but it is actually more generally useful to understand what is up with this population density. So as so often, we start our discussion in reciprocal space, right? And here I'm drawing the two axes, and I'm drawing basically the allowed states here as dots, okay? So these are very finely spaced states. We said they're inversely, their separation is inverse to the number of ions that we have in our crystal. So they're very finely spaced. And then I'm going to ask the following question. If I'm going to draw two energies in here, okay, how many of these states fall within that annulus, okay, between those two energies? That's kind of what I'd like to ask. And so that's sort of the question to keep in mind. I kind of would like to know how many states have an energy of E, let's say, plus minus a certain delta E. So a certain width, we're going to allow for a width here to be able to capture some states. If I just drew a single circle in here, we're assuming the free electron here, so the line of constant energy is a circle, as we know. If we just drew a single circle, well, it wouldn't really capture any states. I need to make that into a ring of a certain width. And so then we can ask how many states fall within that ring. So that's sort of the goal that our initial goal is to find that. So the way we're going to approach it is, as we already said, in K-space, we have the spacing in K-space. So we could say, how do we quantify that? On the homework, we said we can draw a little tiny volume around each one of these states. And so we could ask, okay, what is that volume that each state occupies in reciprocal space? And if you remember the homework problem, it's sort of inverse to the volume that the physical crystal occupies. right? And so we also see that it's inverse to the number of ions that we have in the lattice, right? And if you have more ions, well, then the whole crystal will occupy more volume. So in the end, we get this nice formula 8 pi cubed over the volume of the solid. So it's a tiny space, of course, because the volume is macroscopic and it's now in the denominator. All right, so then we can ask, what is the volume of a sphere of constant energy? So in reciprocal space, the volume would be 4/3 pi k cubed, right? So the volume of a sphere is 4/3 pi times the radius cubed, and here we're talking a sphere in reciprocal space, so the radius is actually a k, a wave number. So we get 4/3 pi k cubed. Okay, and then we also know that the energy is, of course, related to the wave number via this ubiquitous formula. We've seen it over and over again, right? And so I can solve that for k, and I get that a k is basically proportional to the square root of the energy. If I combine this here with that, then we see that we get basically e to the 3/2, right? So basically here I get e to the 1/2, I plug it in to that formula, now I'm cubing that, so I end up with e to the 3/2 power. So that is basically now the volume in reciprocal space of a sphere of constant energy E. So we could say that this sphere encloses all the states that have an energy E or less. Right, the volume of that sphere encloses all of the states that have an energy from 0 up to this energy E. All right, so that's a good and useful little formula here. Okay, and so how many states do we enclose here? Well, we know the volume in reciprocal space that each state sort of claims for itself. Then we know the total volume enclosed by this sphere. The logical thing is to now divide the two, right? And so that's exactly what we're doing. We're going to divide this by that, and that gives us the total number of states that have an energy from 0 up to the energy E. And so we can rearrange a little bit, and we get the volume, the physical volume of the crystal up in the numerator. And then this eta here is just proportional to e to the 3/2. Okay. So as we said, this is the number of states with energy less to or equal than E, less than or equal to E per unit volume. Then if I divide this by the volume, then I get basically this pi over 6 times a constant to the 3/2 power times e to the 3/2 power. Okay, basically I'm just taking this here and dividing by b. Okay, right. So what does that give me? Well, really I'm interested in the following scenario. If I'm at E and I have enclosed a certain number of states and then I increase that energy just a little bit, how many more states will I enclose? Right, and so that is the original question. How many states fall within that sliver of a ring, right? That little ring, that little annulus. So I'm already at E, and then I'm going to go a little bit higher in energy, so E plus some small delta E. And the question then is, how many more states will I have enclosed in that slightly larger circle or sphere in 3 dimensions? So you can kind of see that I can take a derivative here of this eta with respect to E, right? And I'm sort of going to get the answer that way, right? So the additional number of states will be given by this sort of derivative. This derivative times the additional energy. This derivative we call Z of V, capital Z of V, and we're going to give it the name density of states, or state density of states. Okay, so that's a name for it. That's not population density. Here we're going to call it the density of states, right? And so it's very straightforward to take a derivative with respect to energy of that previous formula, right? So the e to the 3/2 then becomes an e to the 1/2 when I do that, okay? And so we see that if I plot it, this z of e against e, well, it's basically a square root function. I've just flipped the axes here. So sometimes conventionally the energy is being plotted vertically, but that's just convention. Normally I would plot this function, of course, with z as the vertical axis and then e as the horizontal axis. And we would just flip this around and get the square root function, right? So that's the important thing to realize, is that the z of e is proportional to the square root of e. All right, so we get some kind of functional dependence like that, okay? And now that we have z of e, the density of states, under control, okay, for the free electron at the very least, we can come back now to the population density, which is what we're really after, the n of e. So one question you might have at this juncture is, why isn't z of e equal to n of e? Why do we make that distinction at all? So why is the z of e, maybe divide out the volume here, fine. Why isn't that already equal to the population density? So why make a distinction between density, state density or density of states versus population density of electrons? Well, the quick answer is because the states may or may not hold an electron in it, right? The states may have one, two, or none. So quick answer is these states could actually just be empty. So yes, there's a state there, but no electron actually occupies that state, so it shouldn't count towards the population density. It counts towards the density of states because there is a potential state there, but it shouldn't count if it's empty. It shouldn't count towards the electron population density, because we have to have that state actually occupied, okay, by one or two electrons in order for it to count. And so we have to introduce another thing here called the probability that a state at this energy would actually be occupied by an electron. Okay, so this probability function. And we call this probability function F, capital F of E. And if I multiply basically what I had before times that F of E, and I also throw in a factor of 2 because a state can actually hold 2 electrons, then I should really get the population density N out of that. So the formula is fairly simple. I'm dealing with a product of the density of states times what is the probability that that state is actually going to be occupied. So we call F of E, we call it the Fermi-Dirac distribution. So it's a probability distribution. And that distribution will depend on the temperature of the crystal. Okay. All right. Let me plot it for you. At very low temperatures, the probability distribution, the Fermi-Dirac distribution, looks like this. It's a step function. And that shouldn't really surprise you from all that we've said before. Because what it says is that at very low temperatures, all states below the Fermi energy are occupied and all the states above the Fermi energy are empty, right? And so if the probability of a state being occupied is 1, okay, and then you run out of electrons, okay, at the Fermi energy, and then all the higher lying states are empty. So it really is just a step function. Everything is occupied, and then you run out of electrons, okay, and then all the other states that might still be available at higher energies are then empty. So we've basically said all of this in words many times. So this is a probability density. So really the probability of a state being occupied is 1 if the energy of that state is below the Fermi energy, and the probability of a state being occupied is 0 if that state's energy is above the Fermi energy, E sub F. Kind of makes sense. Now, at a higher temperature, there's some smearing out going on. Okay, so it's not going to be quite as sharp of a step function. It's going to be more like this. So those of you who've taken statistical mechanics, okay, thermodynamics and statistical mechanics, physics 331, last semester with me, well, this is nothing new. We discussed the Fermi-Dirac distribution. But those of you who didn't have that course, it doesn't really matter because you can learn it here. And it's really nothing too surprising, right? So when you have a little bit of temperature going, then some of these electrons that used to be here can maybe get thermally excited to states that are just a little bit above the Fermi energy. So we smear out that sharp edge at higher temperatures. All right. We have a nice mathematical formula, believe it or not, for that. And the formula, I'm just going to give it to you. In 331, we derived this formula from, well, first principles, really. Here, it's not important for us to derive it. I just want to give it to you. Okay, and the formula is 1 over this exponential function plus 1. Okay. So we could ask, does that really give us the right graph that we saw before? So what I kind of would like to do now is to explore this function a little bit to make sure that it actually makes sense. Okay, so first off, you should see that this function really is bound between 0 and 1. So for instance, it can't go above 1. Why? Because the numerator is 1 and the denominator is always larger than 1. Right? Because the exponential function cannot be negative. It's always some positive number. And so the denominator then is always slightly bigger than 1. And therefore we get this function never, never getting any bigger than 1. And furthermore, it can't dip below 0 either. Okay, if you can, because this denominator can't be negative. Certainly can't be negative. So, if this here gets very, very large, this exponential here, if that gets very, very large, then we have 1 over a very large number, and that could maybe approach 0. And if this exponential gets very, very small, then we approach 1 over 1, which is the other limit, namely 1. Okay, so that seems to work out pretty well. So then the next thing that we want to do here is to look in the limit of T going to 0. So at absolute 0 temperature, 0 Kelvin. When the temperature goes very low, then what does this ratio do? Okay, well, it's going to go, you'd say it's going to go very high. It's going to approach infinity, but that's only true if the numerator is positive, right? And if the numerator is negative, then it'll approach minus infinity. So that's why I'm saying that this ratio here is going to be either plus infinity, is going to go to either plus infinity or minus infinity. So if the energy is larger than the Fermi energy, E is larger than E sub F, then that ratio goes to plus infinity. And so when that ratio goes to plus infinity, then e to the plus infinity is a very large number. And so we see that the Fermi-Dirac distribution f of E goes to 0. But when E is less than E sub f, then that ratio here goes to minus infinity, and we see we get 1 over 1 in that limit, and the Fermi-Dirac distribution goes to 1. And so this is the origin of the step function. Right, that's what gives us the step. All right, here's another thing to point out about the f of E. When we're not at 0 temperature, but at any other temperature, finite temperature, then the energy, the f of E evaluated at the Fermi energy, okay, so we're evaluating it at the Fermi energy, is always going to be 1/2, right, because we get E sub f minus E sub f then here, and that's going to give us 0, and E to the 0 is 1. 1 plus 1 is 2, so we're getting 1/2 at the Fermi energy. It's another property that is worth pointing out. And the final property worth pointing out is what happens when the energy is much, much larger than the Fermi energy. Now at absolute 0, it's clearly just 0, right? The f of E is just 0 when you're above the Fermi energy. But at finite temperatures, at non-zero temperatures, what does the functional form approach? Okay, so we're in this limit of this difference being much, much larger than KT. Then we can say, well, this is the exact formula here, the exact expression. But you can see that if E minus E sub f is much, much larger than KT, then this becomes a large number. It's probably okay to neglect the +1 in that case. You know, if this number is already 1,000, well, 1 over 1,000 is not very much different from 1 over 1,001. And we can sort of drop the +1 and we get just simply that. Okay, and that gives us a nice, a simpler formula to work with. Okay, it's just E to the minus the energy difference over KT. We can also write it like this if you wish. And in that form, we see that we get the Boltzmann factor back. Okay, we get pure exponential decay in that limit. So that'll be something that we'll make use of when we talk about semiconductors in a little bit. Okay, so that is basically all that I want to say about the Fermi-Dirac distribution. But we're now ready to pull all the pieces together, put all the pieces together and see what we get, right? So we said earlier that the population density of electrons is given by this product, where this is the density of states, and then this is the probability distribution for a state being occupied. All right, and so we already saw that if I plot Z of E against E, okay, then I get sort of this square root behavior, okay? And we also saw that f of E is basically 1 all the way up to the Fermi energy, and then it drops to 0. So can we, in our mind's eye, can we take the product, multiply these two curves together? Well, before we do that, just point out that this is for a very low temperature here, temperature equal to 0. And then at any larger temperature, higher temperature, we get more of a smoother transition there, right? And so we get the dashed line. All right, so let's mentally multiply these together. And at t equals 0, it's not hard to do, right? It's this, and then it drops abruptly down to 0. Like that. That would be our population density, N of E, the function of E. Right? It looks parabolic here, and then it drops to 0. So this is still a square root behavior here. Okay, and then at any finite temperature, it would look like, or at any non-zero temperature, it would look like more like this. And here's where we get the exponential tail. Right? So that's all fine and good. Okay, and we can even very easily find the mathematical expression that goes along with this population density. I'm just multiplying the two results from before together, right? So here's my part that has to do with the density of states. It's proportional to the square root of e to the 1/2. And then this is the Fermi-Dirac distribution function. Okay, so it's good to have that in closed form. But one thing to point out is that we really are after the population density at the Fermi energy. So we are more interested in this function here being evaluated at the Fermi energy E sub f. Okay, and when I plug in E sub f, well, this becomes an E sub f here, but this here just becomes 1/2 from the property that we mentioned before, right? So we get this equation here. And basically a whole bunch of constants, but then we get also this Fermi energy. And my last step here is to say a little bit more about this E sub f. What does it in turn depend on? Okay, so what does E sub f depend on? And we could say qualitatively that it should depend on the electron number density n. If there's more electrons, then I need to go higher in energy to accommodate them all, right? So it intuitively should depend on this number density. And so that is actually true, right? And we can actually quantify that a little bit more. We can say that this little n, the total number density of electrons, should be given by an integral of this function here, n of e, from 0 to e to the Fermi energy when we evaluate this at t is equal to 0. Okay, so at t equals 0, there is really this very sharp step. And all the states are filled below the Fermi energy and everything is empty above the Fermi energy. So this energy integral really only needs to run from 0 to E sub f. So can we evaluate the integral? That's the integral that we need to tackle. Can we evaluate it? Okay, and so I can plug in what I know this n of e to be. Okay, you might wonder, where did the second part go? Well, it's just 1, right? At 0 temperature, it's just 1 all the way up to the Fermi energy. So the Fermi-Dirac distribution function f of e is just 1 from 0 to E sub f, and therefore it doesn't appear anymore in this integrand. And so now we can pull out all kinds of constants from the integral, and we're really left with a very simple integral to do that everyone can do in their sleep, right? It's basically the integral of square root of e dE, and we get obviously 2/3 times e to the 3/2, and we have to evaluate that from 0 to the Fermi energy. Fine. We end up with this final result. Okay, and I'm going to frame that. It is also equation 610 in our textbook on page 69. And why did I frame this formula? Because it gives us a relationship between the Fermi energy and the number density of electrons. Okay, or I can also solve that for E sub f, and I get then this formula here. And what we see then is that the Fermi energy depends on the number density, right? And the larger the number density, the larger the Fermi energy, so that makes sense. But the exact relationship is that the Fermi energy is proportional to n to the 3/2 power. Okay. So for free electrons, at least, the Fermi energy is determined solely by the number density of electrons, and more precisely, the Fermi energy is proportional to n to the 3/2 power. So that's actually maybe something that is worth memorizing even, that is that relationship. So the point is now we've got it all figured out, at least for free electrons. We know how to compute the Fermi energy. We know then how the Fermi energy, you can plug that into the population density formula and get that out as well. And then we can plug the population density N of E back into the conductivity formula and predict the conductivity as well. Now, one caveat is that this has all been developed for free electrons. Can we modify it for Bloch electrons? Because in the end, we're interested in Bloch electrons, right? Electrons in the context of a crystal lattice. So how do we sort of modify some of this for Bloch electrons? Okay, so it's actually not that difficult. We have here the free electron result, E versus K, that's just a parabola, right? But we know that that gets modified in the presence of a lattice. We get this energy gap here at the Brillouin zone. Okay, this is here, I'm drawing it in the extended zone scheme. So the idea then is, how does this affect the density of states formula Z of E? Okay, the Fermi-Dirac distribution is unconcerned with all of this, so that stays the same no matter what. But the first part, the Z of E, will depend on the band structure. Why? Because hey, the Z of E has to go to 0 in here. There are just no states available in the band gap. That's why we call it a gap. There are no states available here, and so the density of states at these energies, right over here, needs to be 0. And so if we look at that Z of E, the density of states, now I'm actually flipping the graph around like it probably should have been in the first place. Z of E versus E on the horizontal axis. Well, this is the free electron result. It was just proportional to the square root of E. Well, if I have Bloch electrons, then I get something more like this. Okay, where we have a band gap, and this Z of E drops to 0 in the band gap. And then here's the start of the second band. Right, so this is the first band here. We get a little spike here because why? You could ask yourself, why do we get a little spike here? So that's something for you to maybe think about. It has to do with the band structure, right? The E versus K is becoming that dispersion curve, or that curve, becomes very shallow as you approach the edge of the first Brillouin zone. And so the hint is that that has to do with the spike here. And then here's where the second band starts. All right, so here's a picture that I took out of one of my favorite texts, namely Omar's text on solid state physics. Okay, here's the density of states. Here's my square root of E, okay? But it gets modified for Bloch electrons, and we again see the spike here, and then there's a gap, and then here's the upper band. Okay, so I basically am drawing it the same thing here, so there's nothing new there, okay? But I'm gonna draw it again. So sometimes the bands in higher dimensions overlap a little bit. We said that, right? The lower band and the upper band overlap in 3 dimensions, or in 2 dimensions even. And so we see in those situations that the first band is maybe like that, okay? And then the second band is right here, and they're not separated by a gap like before because they overlap. Okay, and so then what is the combined effect of both bands? Well, you can kind of see that there's the overlap region, and so I get something like that. Okay, so this is sort of the combined density of states from the 2 overlapping bands. Okay, so that can happen quite often. So now let's think of monovalent metals versus divalent metals again. We're going to try to come full circle here. Okay, and so with the monovalent metal, we know that the first band is only half filled. And so here's my population density. This book here calls it little g of E. Our book calls it capital N of E. So I've gone with the notation of our book. Okay, so we're plotting here population density N, capital N of E, all right, as a function of E. And we see again, here's my shape, but I'm only half filling that band. So my Fermi energy might be somewhere in here. Okay, so I have to evaluate this N of E at the Fermi energy. So I'd be picking out this point to plug into the conductivity formula, right? Sigma conductivity formula only cares about the N of E evaluated at the Fermi energy. So this point is what I would be picking out. Okay, now let's take a look at the divalent metals. Okay, so what happens with the divalent metals? So with the divalent metals, we're right in here with the Fermi energy. Okay, so these bands are now overlapping, and I'm somewhere in here. Now, where exactly the Fermi energy is depends on the exact metal that we're looking at, but it'd be somewhere in here. And so what's interesting now is that if we compare to the monovalent case, there can be a situation where the population density at the Fermi energy from before is higher than what it is now for the divalent metal. Okay, and so we have here an explanation for how a monovalent metal could be more conductive than a divalent metal. This is the thing that didn't make sense, really, that didn't make much sense in the Drude model. You know, from one point of view, we might say that divalent metal has a lot more electrons floating around compared to the monovalent metal. But this new formula for conductivity really only cares about the population density at the Fermi energy. And so it's very clear how we could get a larger population density in the monovalent case compared to the divalent case. Okay. All right, so this really concludes my discussion of metals, and we're going to turn to our next big topic next time, namely semiconductors. All right, so stay tuned. Thank you.